month. So for the people in workshop, we have each month a colloquium broadly on data science, gathering together mathematicians, physicists, computer scientists, and neuroscientists. And so on. We're very happy today to have Wolfram Pernis from the conference. And after the talk, there will be an open buffet just there where we had the coffee break. Thank you. I hope it's coming back.
I'm not really sure what's happening right now. It's doing all kinds of crazy things here. Okay. Okay, it's probably best if I don't touch it. Okay, yeah, thank you very much for the introduction and also very much for the invitation to come to Paris. It's always a pleasure. Yeah, I'll switch gears quite a bit compared to the previous two speakers, since they are, I think, the only biology that's in there are probably the PhD students on the last picture. And other than that, it's mostly about computing. And so really what we do is we try to find new architectures for implementing accelerators for processing big data sets. And there's, of course, the prime application in artificial intelligence, where a lot of data processing is required. And we try to build things that don't work like a conventional computer with electronics, but rather with optical systems. So what we implement are these waveguide-based devices that process information at very high speeds, but they only do very basic information processing. So maybe the title is a bit bold, since the only computing that we really do are very basic arithmetic operations, but nevertheless, those we can do very fast and hopefully also energy efficient. So I think it also fits in the scope of this conference. And to get us started, I'd like to motivate it a little bit with progress over the last 12 years or so. And a lot of that came basically from games. So one that I always like a lot is this game Jeopardy that the IBM Watson engine was playing. So you can see IBM's system down here. It's a big server rack with a lot of CPU, central processing units, the same stuff that you have in your personal computers or in this laptop or such, and a big amount of memory. And with the artificial engine that was running on the system, air-cooled, of course, with a big AC, so most of it is actually air conditioning that you see. This system was able to make sense of spoken language already in 2011, so many years back. But it did so better even than the human contestants that you can see here, Brad and Ken, some of the guys that play this game Jeopardy very well. So you need to make sense of language. But Watson did even better, so you can see it on the score here that he beat these two human players with the help of this engine, but of course at the cost of energy. So this air conditioning system uses about 80 kilowatts of power. There's a lot of dissipation in electronic systems, whereas the humans consume the roughly 20 watts or so that the brain is basically powered by. So there's a big difference. And this was not a neural network yet, but a different type of algorithm. So our modern AI systems perform even worse in comparison at one specific task. Games, however, have been driving the field quite a bit. So there's just a few examples from recent literature, also some that I used to play many years ago. StarCraft was one of them. There's basically no point anymore, since the AI is so much better than any humans. And the same holds for other games. So this is one that my son plays. Also no chance against a machine anymore. And this came out very recently, last Friday. So it's basically a board game, but there the AI system has to interact with humans in spoken words. So in an online version of this board game Diplomacy. And even there, the AI was able to do really well, so is in the top %. And most players were not able to basically tell that there is an AI system in the background, but they thought they were playing against another human player. So a lot of progress, but there are also other things that you probably know. So for example, there's this Dali system from earlier this year. So this engine, you can give a sentence, and then it creates a picture from it. So, for example, here this robot arm hand doing a drawing in a digital art, and then this is what it gives you. Or these, I'm afraid they're in German, like a leopard sitting in an armchair reading the newspaper. Then you get this Hamburg Skyline with lights and so forth, or even Renaissance paintings. And it's all created from scratch using a very powerful neural network engine that's working in the background. Very recently, which you probably also have seen, is this ChatGPT-3, and I like this a lot. So just for fun, I asked it write me a research proposal about neuromorphic hardware and superconducting detectors, so two of the things that we do, and then it comes up actually with a pretty good research plan. So it gives you the idea what it should do. It gives you the milestones, the work packages and everything, and also some outlines. So that might be a big help for proposals in the future, but also maybe a bit scary, since then we kind of become obsolete in some sense as well. So there's a lot of progress, and this may be toys, you might think, but there are also other examples that are maybe closer to real life. For example, autonomous driving. So this is not so much playing games or creating proposals, but rather making sense of the environment. And here's one example from a car manufacturer that we work with. So where they're basically, it's an electronic golf system that is driving through inner city. So really in real traffic, the driver has to have the hands close to the steering wheel to intervene if there is some problem. But you can see that the engine basically, I'm sorry for the poor quality, makes sense of the environment. So you see kind of on the computer what it recognizes, the other cars here, moving traffic lights or trees or pedestrians or such. And by recognizing these objects, it makes sense of the situation and tries to react accordingly. And that works pretty well. And most of the time, the driver actually doesn't have to touch the wheel, but can sit driving. And of course, this would be really nice for being on the highway at least. But it also works in this complex environment. It doesn't work so well if something unexpected happens. For example, if it sees a train, so a very big system, this confuses the engine actually, and it doesn't know what to do. So it's good that you have your hands close to the wheel in these cases. Or if there are some other structures that it's not familiar with, then you have to be a bit careful. But I would say that it works fairly well already. So this is object recognition and detection, and also making sense of complex situations. But again, it comes at a cost. So if you look at the trunk of this EGolf, then it's basically full with electronics and a lot of computing power. So actually 3 GPUs, general graphics processors, are powering the system. They are somewhere at the bottom here. And they also need to process a lot of images that are retrieved from the 5 cameras sitting on the top, the LiDAR systems, the radar system. So very fancy electronics that monitor the environment. But this, again, draws a lot of power. It's not 80 kilowatts, but it basically empties the battery of this EGolf in half an hour. And that's not so great if you want to drive somewhere. Of course, you may not need all of this. This is research overkill, but still it limits the mileage of such electronic cars quite a bit. And therefore, for the manufacturers of such systems, it's a real problem, because the current electronic hardware is basically not doing what they really want to do. So basically give the power to the engine and not just to the computer. Yeah, and the problem sort of that underlies this story in general is the way that modern processors are built, or at least the vast majority of it. They are based on the von Neumann architecture perceived by John von Neumann in the 40s, so during the war. So he basically developed the blueprint of an artificial computing system that is able to process data. And he actually wrote it very much in the way of the nervous system. So he talks about different types of neurons, synapses and connections inside an electronic system that sort of processes information in a way similar to the brain, even though the actual architecture is not so similar. So basically the way it works is there is a very powerful central processing unit, so a chip system that is good at complex arithmetic. You have a big instruction set in your computer that is good to perform these functions, but only on a limited amount of data. So this is basically the trade-off complex functionality, but on short bit streams. And therefore, also, I did something.
I just unplug, replug.
Unplug and replug.
Unplug.
Okay.
React. The computer is there.
Computer is still there. This is not. Okay, let me try to go out.
Look at that level. Computing.
Which one?
That level.
Oh, can I unplug this too?
No, it doesn't do anything.
So maybe if I stay too long on one slide, that's a problem.
Or with that you press something here or
Here?
no? I wonder a bit whether yeah, I might.
I'm not really sure.
Yeah, I'm no idea.
Yeah, then I. What is it?
We want to try another computer.
I went out of the presentation mode and this is.
Okay, so I'm out of the presentation mode too.
Oh, we can try another.
Can try that too.
Yeah, try.
Maybe I won't use the presenter.
Yeah, maybe we'll just try another.
Okay. It recognizes the projector, I think. Sorry about this. But I don't think it's on, right? I don't see there is any light coming out of it. Yeah.
We depend on it.
So I can give a chalk talk, but it's probably not so good for the whiteboard. Or is there a way to... Did I press something wrong here?
No. I think it's there is a problem with the projector.
Okay. Huh. So I can turn this around, but you probably could not see so much.
So the projector went down, so Juju has gone to find another one. But,
Okay.
oh, okay, no. So what happened?
Ah, yeah, there's a light. Okay, let me unplug this.
You did something? No.
Yeah, I mean.
There is a blue light.
Now it's on. Maybe
Should I?
Yes.
Yeah.
Should be. T'es sur PC? Oh non. Il faut un certain temps pour qu'il se rallume.
So it switches to the...
For the light to come back.
Okay.
Because we don't see any light. It's only the fact that the bulb is actually not working anymore.
Okay.
So I think Julia went to get the other. So we get another one. Sorry.
No worries.
So it's coming. We'll take a couple of minutes.
Okay.
It's on, but there is no light coming out.
But now there's something.
And the way it was switched
Ah, we're back. Ah, very good. Cool. So I won't touch any of this, but rather touch the keyboard. Maybe that helps too. Yeah, so basically what you have to do is basically shuttle data between the memory and the CPU all the time. So your big data sets are stored here, you process them here, and you move them down and then up again. And of course, this is the bottleneck and also what is power hungry, since processing inside the CPU is actually cheap, but memory access is the expensive bit. And of course, in the brain, as we heard in the previous talks, this is done differently. So there you have your memory directly at the location where the computation is also done. So it's co-located, and therefore, in principle, the brain does a very nice way of in-memory computing, and you avoid this shuttling, but need a different architecture that is highly interconnected. Of course, this is exactly what you need if we build these artificial neural networks to do classification. So this is one example of how this works. You have some image that might come from your car's camera or so, and then that is passed through your favorite type of neural network architecture. For example, a simple deep feed-forward network where you encode each pixel on a different input neuron, and then it's passed from layer to layer through a cascade of interleaved interactions. And basically what happens between the layers is linear algebra, so a lot of matrix vector multiplication, so relatively basic instructions, but you do this in a sophisticated way combined with the architecture to classify whatever is in the image. So typically you take the image into different type of colors, for example, in the first layer. Then you have 3 data sets that are passed through. On each layer in these convolutional neural networks, at least you apply an image kernel to, for example, detect edges or other features, create feature maps out of them, and then by the end it goes into a fully connected layer to do the actual classification. And now the trick is to pick the right hardware. You can do this with a standard CPU as in the computer, but this is probably not the way to do it, and therefore a lot of effort is spent on building dedicated hardware like these graphic processing units, GPUs, as were in the Golf car, or also entirely dedicated units like Google's Tensor processing computer or such. Okay, yeah, so then if you build this in this specialized architectures for this very specific tasks of, for example, matrix vector multiplication, the hope is at least that you can go into a very different regime of operation, and one sort of dream goal is there to reach 1 femtojoule per operation. This is still relatively far from the estimated energy per operation in the brain. This is on the attojoule range, maybe. The biologists probably know this much better. But at least there are some orders of magnitude that can be bridged by going away from this decentralized way of computing. Basically, the message is the further the memory is away from the actual processing, the more costly it is. So you can see different types of memories here. DRAM or so, then you have energies on the order of 40 to 100 picojoules, for example. If you go to onboard memory like SRAM or flash, this is reduced already by an order of magnitude or such. But if you basically incorporate the memory directly in your processor and go to these in-memory processing units, then you are in a regime where this becomes feasible, and hence also the energy demand goes down in the end. And this is actually a big challenge because the overall energy used on the entire globe for ICT, so information processing and communication, grows very, very fast. And if there's no good idea what to do in the next 15 years, then 100% of all this energy goes towards computing, which is probably not good in the winter when it gets cold or such. Okay, so yeah, at the heart, as I mentioned, are some basic operations, and they are basically often matrix vector multiplications, which is also why we focus on this particular operation. So again, if you have this feed-forward network or such, then you take your input neurons and you map them onto your next layer, and this mapping basically corresponds mathematically to a multiplication with a matrix that contains the weights in this neural network. That is multiplied with the input vector, so the image data, for example, or some other smooth function. And then you might also have to add an offset if you have some bias or such in this system. And therefore, if you want to do this efficiently in the computer, this is basically what you need to build, a unit that performs matrix vector multiplication at low energy and high speed. And the nice thing is that it doesn't have to be very accurate. So it can also be done in analog implementations. You don't really need to work in the digital space, even though that is good. But if you have the flexibility to go to other ways, you can there also make benefits of computing architectures. Okay, so what Google, for example, does in their tensor processing unit is to encode this weight of matrices, or this matrix with weights, directly on the chip in such a systolic array. So the idea is basically to go halfway to in-memory computing. You store one component of the multiplication locally, and then just pump sort of the data stream through, so your image data. This is also where the name comes from. Systolic array means sort of pumping like a heart kind of system. And the idea is that you have your matrix there, and then you just pump your images through, and therefore reduce at least one bit of the memory access, since you don't need to fetch the weights from memory, but you only need to get the image data from memory. This works already very well for this particular task, but is still somewhat limited in speed. And therefore, a lot of effort is also spent in coming up with new architectures or building on existing architectures to implementing exactly these specialized hardware accelerators for matrix vector multiplications. As I mentioned, you can do this with analog data. This might be beneficial also in terms of energy savings. And here are just 3 electronics examples that are investigated at the moment. You can use the flash memory that you already have on your computer and just implement the weights and the computation in there in this transistor architecture. You can also use the SRAM, so that is close enough to the central processing unit as well. Or with new architectures like these memristors, which are quite popular. Those are types of materials that can store not just one bit level, but many of them. So you directly have a sort of analog data, and that might map nicely to kind of a matrix multiplier inherently. And you can also see from this crossbar architecture that it looks a lot like a matrix. So you can imagine if you put your image on the one side and collect at the other side, then you have sort of this in-memory architecture that gives you benefits in terms of computing. Yeah, okay, but as I mentioned in the beginning, we want to go away from electronics entirely to optics. And there you can do very similar things. Basically do analog computation in optical systems. And in principle, it's similar to what electronics does, but just that the carrier is no longer an electron, but rather a photon or a particle of light. And this has some obvious benefits. For example, it's quite fast, right? So the signals move at the speed of light through your system. But you also have the benefits that on light fields you have different degrees of freedoms that you can exploit in such systems, which make it powerful in terms of scaling. For example, you can exploit the color of light. Different wavelengths don't talk to each other in such a system, so you can imagine that you can send all of these different colors through one architecture and therefore calculate in parallel. You can also use polarization, for example, or spatial modes and such. So there are many degrees of freedoms that you don't have in electrons. The drawback, however, is that your system becomes a bit more exploratory and is not as established as a manufacturing architecture, and everything gets much bigger. So you can see some examples of what people have done in the recent year. It's sort of very loosely grouped in 2 types of architectures. This one here uses free space optics. So it's not a chip system, but something that works with more traditional systems like lenses and beams. This is very nice in terms of parallelizing things. For example, these diffractive networks here have different types of filter architectures that send one big image through at the same time. So you can sort of map this directly to image processing and recognize what is on the structure. This is great, but it's mechanically a bit more challenging. So the other option is to go to chip-based systems. That is the bit on the left-hand side. There are also different types of architecture. Some of them I will show you. that use sort of ring resonators and lasers, for example. You can have also more exotic ones with superconducting structures. These are very promising in terms of super low energy consumption. And then also these artificial neural networks that work with a waveguide architecture. Yeah, let me sort of tell you briefly why this all makes sense. So if you just look at performance, then you don't win much, because essentially you have the same factors that you also have in an electronic system. The number of operations that you can do per second scales with the frequency. So the faster you send your data through, the faster your result is there. And of course also with the number of elements. So if you have a lot of computational units, then you get a lot of computing performance. But this is exactly the same as an electronic system, or this tensor processing unit that I mentioned. The benefit comes if you look at the way that you can implement these architectures. So for example, if you take this systolic array, so this matrix that is sitting on a chip, you can break this up in different subfields, and each field calculates a part of your big matrix. But basically this just scales linearly with the number of submatrices that you use. If you break one up into 9, then you have 9 times less, 9 times the size of the array, so 9 times the energy consumption. But if you do the same with a photonic array, and you break it also up into these 9 pieces, then you only need to send in the data from the sides. So it passes through at the speed of light, and you need to detect it at the other end. So therefore, the power consumption doesn't scale with the size quadratically, but rather with the number of edges, and therefore you just have a linear scaling. So it means that if you make your matrix processor bigger, then you win eventually, because your scaling goes up in a linear fashion, whereas on this electronic system it goes up quadratically. And therefore there is a sort of fine line where this starts to make sense. You have to go to decent enough sizes, but if you do, then you have a nice knob that you can play with to increase your power efficiency. Okay, so how do you actually do this? I sort of alluded to it a little bit. You make these little computing units, then you send your light fields through, and your processing is actually measuring the power that comes out at the other end. And if you put this down in terms of numbers, then you can sort of make a rough table. This is maybe not the best comparison, but it sort of gives you an order of magnitude where there is room for improvement. Of course, if you argue with other researchers that work in different domains, they don't like this a lot. So it has to be taken with a grain of salt. But at least from an optics point of view, I think there's room where you can win. And one is the time that it takes to go through such a system. So this is called sort of the latency, the time that it takes to get a result when you send it in. And for an optical system, this is, as I said, at the order of speed of light, so roughly 100 picoseconds. In an electronic system, this is on the order of nanoseconds. So there you have a few orders of magnitude that you can push through. A big factor is the bandwidth, so how many channels you can basically put in your operation frequency. In a photonic system, this is easily on the order of tens of gigahertz. In an electronic system, probably a few gigahertz. So your processor basically always operates at 3 gigahertz range or so. There you maybe win a factor of 10. Power is a big issue because, as I said, one scales linearly, the other one quadratically. So there I think you can win quite a bit, about 3 orders of magnitude or such. You don't have any benefits in the area because photonic structures are usually big. Transistors are very small, so you can pack a lot of electronic components in a small area. If you build the same thing in photonics, it's much bigger, but you have these additional knobs that you can play with. If you take them all together, however, I think you see there is a long-term at least benefit to be won. So if you want to design a powerful system, this can be done very nicely with optics. So how does it actually work? I think if you want to build one, you have to sort of start with the elementary blocks, and that is a very small multiplication. And the smallest multiplication that you can build in an integrated system is this thing here. It's an interferometer where you send in light from 2 arms. Then they interfere with each other by coming to this beam splitter. You can adjust the phase, and then they recombine. So basically what this little interferometer does is kind of it rotates the light field a little bit. And if you put your input as 2 numbers, then what you get out is a mixed system of 2 other numbers. And the matrix that this structure implements is basically the one on the right-hand side. So this is sort of a rotation. I think the physicists know this very well. This is what you see in your basic quantum mechanics lectures, where you rotate also some spins or such. Yeah, you have a question?
What object would be the phase shifters? Is that a crystal or something like that?
Yeah, there you can use your favorite way of shifting phase. For example, if you work in a silicon system, you can adjust the refractive index by heating, by injecting carriers, or by modulating with other structures that you bring close by. In principle, it always corresponds to changing the refractive index of the waveguide, and there are nice methods of doing that also at very high speeds. So you can go to a foundry, then they have different building blocks and they give you exactly these elements, so beam splitters, waveguides, and phase shifters, and those you put together, and then you have your basic computing unit to perform such a multiplication. Yeah, so basically this is what you can play with, and then you go to a design house and you make it big. So this is one example from MIT that came out a few years ago. This is a matrix processor that works all optically. I don't think it's very easy to understand what's happening at the top, but if you take sort of a small section, then you see what I showed you on the previous slide. It's an interferometer where you basically have this beam splitter, then 2 phase shifters, and you combine again. So this is then the rotated matrix multiplier that you get in the end. As just explained, on the foundry you can buy components that do exactly this, so the phase shifting, and then you have to inject light from the input, measure it at the output, and if you cascade a lot of them, you get basically a nice matrix processor that works now all in the optical domain. And in principle, this is already going into commercialization. So for example, Light Matter uses such an optical processor. There you can see there is a photonic chip in the center. It has input from a light field, so this is basically going through this fiber strand onto the photonic chip, where you do exactly this matrix multiplication. Around of it is a lot of electronics, because in the end, of course, you want to talk to a normal computer, and you also need the electronics for doing the actual analog signal processing, so encoding the input vectors, decoding the output vectors, and interfacing this all with your favorite AI architecture. However, it basically shows that it's possible, and it's not just possible in a lab, but also if you have enough funding and smart people to build this as a board system, then you can process in a co-integrated hybrid electrical and optical structure. Okay, so this is nice, but it's complicated, and therefore we try to do it more simply. And I think you can very intuitively understand how you can do this multiplication also in a different way if you just need to encode 2 numbers in different ways. So what we do is we take one laser to encode one number as the amplitude of light. Then we take another method for attenuating this laser, so setting kind of the transmission through a device. And if you want the result of this multiplication, then all you have to do is measure the power. So basically look at how much light comes out at the other end, and you also performed your multiplication. And this is nice because it only needs 3 components. You need some laser for setting the amplitude, so this could be such a fiber-coupled structure that you can buy off the shelf. You need some chip to set the transmission. This is what I'll show you in a second. And then you need something to measure at the output, so this is also something you can buy. Again, a fiber-coupled component that is quick. And because these are optical systems that have been optimized for telecommunication, they operate at extremely high speed, so you can easily go to these tens of gigahertz that I mentioned. What you need to design is the chip that sits in the center, and this is essentially what we do. Okay. If you want to now modulate the amplitude, you can buy these foundry systems, or you can use something that somebody else developed, and this is what we do. And we take a so-called phase change material. I mentioned this already in the membristors, but it's also something that you all know. It's basically the stuff that sits on rewritable DVDs, or at least the older people know this still. Now, I don't think there are any CD drives in any computer anymore, but nevertheless, It's this what makes the colors shine on a CD. There is a little layer of this phase change material, and what it basically does, it changes its refractivity by changing the crystal state. So if you have kind of an ordered crystal structure as on the right-hand side, then it behaves more like a metal. This is sort of the refractive index that you can see here. It goes up quite a bit. It becomes very absorptive, that you see in the imaginary part. I mean, this is not a phase change material, but a metal. But you get the idea. It becomes opaque. If you then switch it from this crystal into something disordered, then it behaves more like a glass, and glasses are transparent. And then you can see here that the absorption goes down by quite a bit. And this is essentially what you do on your DVD. You locally change the reflectivity to implement a bit or multiple bits in such a structure. We just take, as I said, something that is available commercially. So it's this particular phase change material, GST. It's one out of many. There are way more optimized structures available as well. But this you can buy, and it comes as a nice target. It's very established. And you can switch it very quickly with optical or electrical pulses. So the way we use it is we take this, put it on our waveguides. I'll show you how this is done in a bit. So there's a little patch sitting on top of the waveguide. And now we try to switch the crystal state of this little patch by using optical pulses. So if you want to know which state it is in, then you can send in a light pulse. So this is the laser from the laser diode that I showed you earlier. And we measure how much light comes out on the other side. And so if you plot this over time, you get a signal like this. If the laser is off, you have nothing at your detector. If it's on, then you get a big spike, and you can read out how much power that is, depending on how good your photodetector is. This is if the material is glassy or transparent. And now if you make it crystalline, then it becomes more like a metal and is absorptive. And so if you send the same laser pulse in, you get a different type of signal out, namely a pulse that is much smaller. Some of the light couples to this phase change material in the near field. It is absorbed, so it's missing in the end. And therefore, what we can play with is this contrast between the two, which is basically the bit storage that we have in this particular material. You also need to encode your bits, and for this we write it with a much stronger light pulse. So what actually happens is this material melts physically, so it gets very hot, about 650 degrees Celsius, but in a very small area. So if you now plot this function over time, it gets hot very quickly. Once the laser is off, it cools down very fast, and therefore the atoms that were molten in this intermediate state, they don't have enough time to reorder, and therefore they get into this amorphous or glass-like structure. This was the transparent regime. If you want to go back, you need to do this a bit more gently. So you again heat it up so that they melt, but then we kind of keep it warm with a smaller pulse, and that means basically that the atoms have more time to reorder. So you give them the time that they need to basically recrystallize. Therefore, you can erase this little amorphous patch that was in the structure in between, and hence you can go back to your original state. The nice thing about this principle is that if you are finished with the process, everything is stable. So you only need this power for writing or reading, but other than that, it remains exactly as is, which is of course what you want on your DVD. So you write it once, and then you can read your DVD a decade later. And this is exactly what this stuff does as well. It's very stable for many years, and you can switch it also over many times and do so very fast. Okay, so then we make use of photonics, and as I mentioned, there are different degrees of freedom. So if you can do this on one laser, of course you can do it also on many other lasers and send all of them in parallel through the structure. And then you can imagine that each of them encodes a number. So your calculation is not just one number that you get out, but as many of them as you can fit in a single line. And this is what makes it powerful, because you can scale very quickly to very fast speeds and also very large throughput. In the lab, we built this by going into the clean room. So actually the students do. They draw these waveguide structures on the computer. This is kind of what you see on the left-hand side, which is what we call a photonic circuit. It's roughly 15 millimeters in size, and you can see this is big compared to a transistor. The only thing that is thin is the waveguide. That's about a micron or so. We take this, translate it into machine format, then go to the electron beam writer. That's the machine on the top right under yellow light, even though you don't strictly need it. Then this is written in a resist and then etched with such a dry etching system. So you transfer it into your favorite semiconductor. This can be silicon, can be something else. And if you do it carefully, you get out exactly what you designed. It takes a lot of time to optimize this, but if it's done properly, then you can get pretty much what you want. So basically, all you can think of at the computer and draw with polygons, you can later get on a chip and therefore do your experiments, but also with just waveguide structures. Light propagates through these lines here, and you can see that we also have these types of interferometers that I mentioned earlier. So this kind of is a multiplication in a sense. There are also other features like these little triangles. They are used for getting light in from a fiber, and you can take it also out with a fiber, similar to this light matter chip that I showed earlier. But in principle, it's a very simple platform. And then we do a second process where we open little windows on the waveguides and deposit this phase change material. And once that is lifted off, then you basically have this computing circuit where calculation and readout are done in the same location. So to implement now a matrix multiplier, because so far I only talked about one single number, we have to come back to these different colors of light and bring everything together. So here's probably the smallest matrix multiplication that you can do. So it's a 2x1 vector times a 2x1 matrix or scalar product. And the way it is done is we send kind of the blue pulse in one waveguide. We have one phase change material here in one particular crystal state. If this is transparent, then the light pulse comes out unattenuated at the other side. And then there's sort of a second waveguide with a red light and a dark phase change material. So this is metallic, and therefore this light pulse gets attenuated, so it's kind of smaller. Then we bring the two together. So both of them are propagating on this bottom waveguide. And now what you have calculated is basically the product of these two high intensities times one high transmission and one low transmission. And if you read the power at the bottom, you get just the total signal, so the addition of these two signals, and this is exactly the scalar product. And pretty much the same thing also is how it looks on a chip. So this is the same structure. It calculates this 2x1 matrix multiplication. So one input here, one input there, then two phase change materials. There are these little gray lines across the waveguide. You see it's a very simple system. The number that we actually want to calculate is set with this two-step pulse that I mentioned before. And now if you know your input power on both inputs and you measure the output, then you have calculated exactly this scalar product. So a very small matrix vector multiplication. Then you want to probably scale this up, and this is what we did next. You need some light source that gives you a lot of these different colors. And there is such a nice light source. It's a frequency comb. You can see here. It's a little micro-ring resonator that is a nonlinear element. If you send a strong light pulse at one color into this ring, there is a nonlinear mixing, four-wave mixing, and that generates a spectrum of equally spaced lines from one single input, which is exactly what we need, because then what comes out here at the output is such a comb of lines with different colors. And out of those, we can pick the ones that we want and then encode that as the input to our system. So we take the spectrum, we separate it spectrally with a demultiplexer. Then each output is going through an element that sets the amplitude. This is an electro-optical modulator. It's actually exactly this one here with two fiber ports at the input and output. If you want n of them, or in this case 4 of them, you buy 4 of these and set the amplitude on each with a voltage and then feed it into a waveguide. On this waveguide, we then have these little bends that connect one light from the horizontal to the vertical line. And here sits the phase change material, which encodes basically the coefficient in the matrix. In this case, there are 4 of them to implement 4 numbers. So we multiply 4 input colors times 4 phase change numbers, and therefore get the scalar product between this input vector times this one column of the matrix. Yeah, and if you can do 1, you can do 4, then you have a real matrix, and it looks very much like this crossbar memristor system that I showed you earlier, just that here everything is done with light. And now, if you're clever, you don't just use 4 of these light fields, but more of them, and therefore parallelize in this scalar fashion. Okay, and this is what the very clever postdoc did. And with that, you can do some image filtering as you need for neural networks. Of course, this is very basic. So here are just edge detection filters. You have some original image, and then in this image, you want to find certain edges. This you can do with small matrices. And what it does is basically it highlights certain areas here on the edges. So you can kind of see that here this one becomes dark on the left side and bright on the other side. Here you can do the same for top and bottom, and then inverse, so right side and left side. And now if you combine all of these 4 images into one, but basically what it does, it finds the outline of the structure. So everything becomes black except for the lines here. And this is kind of one of the first steps you can do if you want to do very simple classification of images. And of course, the classical one that everyone does, if you don't want to put too much effort in, is handwritten digits. So in this database, this is maybe not the best example because it's almost linearly classifiable with very high efficiency. But nevertheless, you can use it for calculating these optical matrices on it. And it does so quite well. So if we process these images through our photonic machine and go then to a fully connected layer, then it recognizes these numbers also with relatively good efficiency, which is not surprising. But the nice bit is that it does this extremely fast. So we can do 4 of these inputs in parallel, limited by the multiplexers. We modulate them with 14 gigahertz. So if you take all of this together, then this gives you roughly 1 tera-Mach operation per second. Well, so 1 Mach is 1 multiply accumulate, so 1 multiplication and 1 addition, which corresponds to about 2 tera operations per second. But it's a fully passive chip, so a lot of the stuff that is important is actually hidden from it. And therefore, we then grab into the box of photonics to make this a bit more integrated. I don't really know how I'm doing with time, but.
You were interrupted at some point.
OK, yeah, I'll stop very soon. So basically, what we then do is we also put the multiplexers on the chip, and I'll show you in just a bit why this is important, so that you can process many colors in parallel. So this we can do with such structures here. All of this at the bottom is basically used for separating these wavelengths into different colors. This one does 4 colors at a time. So you go in with 4 at the same time, and then you get 4 different colors out at the output. You can already see this takes a lot of space. And the matrix is basically only the small part here at the top where we can program the weights. However, this system is nice because it can do both positive and negative weights by using a balance detection scheme. So you can basically combine more elements on your chip. And we want to do this because if you go to the lab, basically the chip is really the smallest bit. You cannot even see it. It's hidden behind the multiplexers. This stack here of plastic with the yellow fibers, this is all done for separating these wavelengths. So you can see you have to buy a lot of those. This thing at the front is the frequency comb. Also, there's a little chip down here, which is the smallest bit, and the rest is electronics, amplifiers, and controls. These are the photo detectors here. You need an optical table to put everything on there. So it's quite big, even though the chip is small. You can make it a little bit smaller. So we did this for Volkswagen. This is our next generation. It's also not super small, but you can at least sort of see the chip here. It's hidden under these fibers again. So this is 1 by 1 meter square, and it's heavy enough so that you can just lift it. So they wanted us to build a photonic processor. So the students kind of did this. And then I told them, well, if it's a computer, it needs to have some lights. So they bought these LED lines and attached them all over the structure, which had this great effect that when it was put into the conference hall, it was sort of like a beacon with lighting up everything. So everyone from the management came basically to look at this processor. even though the chip is really just this little bit, and most of it were the lights actually. Not very energy efficient, but it had a good show effect. But still pretty big. So therefore, we're trying to make this even smaller and put everything together. Therefore, you need different chips. So laser sources here, each with a little comb. The modulators you can also integrate with indium phosphide. This is an active platform. And then if you connect them with these 3D printed structures to these matrices that I showed you, then basically it kind of fits into a little package that maybe someday can sit on an actual chip. Okay, so this is what you then get. This is a indium phosphide chip where you have the matrix in the center, actually 2 of them for reference. You have the lasers up here, the detectors down here, the modulators in front, and here you also see these little multiplexers. So it basically does, again, just this 4x4 matrix. But in principle, now you have all the active optics on one chip, and what you need is smart electronics underneath. This is actually the difficult bit, and I have no idea how to do this, but maybe some smart company can do so at some point. And if you do this, then you have sort of an optical processor, which Herbert Dies was quite excited about. Unfortunately, so this is the guy that we wanted to lure to this system with the lights and everything, and he actually came and said, yeah, these optical neural networks are very promising and blah, 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 could be the future. But then a few weeks later, he was gone, so there's no management, and now we have to try another trick for the next one. But nevertheless, there is some hope that someday this might be useful for something. And with that, I'll end and just thank my group. You can see them here from earlier this summer, a lot of sponsors and a lot of great collaborators. Particular Harish in Oxford does a lot for the phase change materials with us. The frequency combs we get from Tobias Kippenberg in EPFL. We work with IBM on the architecture, and David Wright at Exeter does a lot of the theory for that. And here I stop, and thank you for your attention. Sure.
So when do I get one in my lab?
Yeah, this is, you can have a chip anytime. But processing probably takes a lot longer, and the difficult bit, as I mentioned in the end, is really the electronic interface to these chips, because these analog systems require AD and DA converters at very high speed, and those elements are also the ones that really draw a lot of the power. So optics is very energy efficient, but electronics at the edge, that is actually a big bottleneck. And it's also difficult to get them in large numbers and at high speed. But if some smart engineer can build a chip that has many of these and good interfaces on a photonic chip, then it's not so far. Whether this is useful, this is a whole different story. Since the precision of these systems is not super high, so we can do about 4 to 8 bits or so, which is enough for AI applications, but not for any sort of general purpose processor. And for that, you would need an entirely different architecture. Sure.
Maybe very naive or realistic, but does heat, is there a
So the heat comes basically from absorption that happens in these waveguides. They never are perfect, so they have losses on the edges. They're a little bit rough, and therefore they radiate. And this is basically the dissipation that we get there. They don't operate at very high power, so the input is typically on the order of milli or microwatts, and that's roughly what you get also at the output. So I would say the optics part is fairly cold. But of course, your driving electronics gets hot very fast. So if you do these AD conversions very fast, that draws quite a bit of power. So your ASIC underneath is hot and the photonics is cold. And you sort of have to balance where you really want to hide your speed in the end.
The question? So I had one question about, the example you gave, the weights you showed were somewhat binary, right? With metal or glass.
Yeah.
So how continuous can you be? Can you?
Yeah, this is of course also a very good question. And the way it works is that you don't crystallize the whole structure, but only parts of it. So I had sort of this sketch where you see this little island in the middle of a matrix, and you can kind of control the size of the island by programming it appropriately. So that makes it really continuous. So yeah. So you have some noise on these levels, but today there are about 64 levels that you can do reproducibly, also within detection efficiency. And if you are smart with your approach, you can even do more. So in electronics, they have a lot more levels that you can implement. So I think 8-bit is probably doable. But in principle, it's an analog fashion, so you can control your transmission to any value in between. And then you just have to read it out with the required precision. So you have noise from the lasers and the photodetectors and such.
No questions? No, so maybe if you have ideas about more questions, then we can do that over the buffet here. So
That's
thank
a
you very
great
much for
idea.
your time.
Thank you.